we can look at the concentration of reactants and products that are at equilibrium mathematically. And when we write the concentrations at equilibrium mathematically, it's called an equilibrium constant expression. Every single balanced equation will have its own formula for representing the concentration of the products and the concentration of the reactants. How we derive the equation is up above. You don't really need to know this, but I just want to explain where it's coming from. So in a very simple reaction that is reversible, because you can see those double arrows, we have the reactant E making the product F. Well, if E is forming F at the same rate as F is forming E, I can get these two equations. K is what's known as a rate constant. So it's just a number that helps you cancel units. So the rate of the forward reaction is equal to some rate constant times the concentration of E. And then the reverse reaction is some rate constant times the concentration of F. And if you know that these two are equal to each other, then we can put the other parts of their equations equal to each other. And then putting the products on top and the reactions on the bottom and getting those rate law constants, those K's on one side, we can make what's called an equilibrium constant expression. So the important part that you need to know is right here in this box. So that K is called the equilibrium constant. It can be a K with a EQ, which is a general equilibrium constant, or it can be represented a KC. When you have these little KC, that means that you have your products and reactants in molarity units, or they'll be in brackets. Remember, brackets equals molarity. Now, this equilibrium constant expression, I wrote it a little bit weird, just so that you know that when you put the products and the reactants on the top and the bottom, you're going to multiply them. If you have any coefficients at the beginning, you are going to raise them to that coefficient. And I almost feel like it's easier to explain how to do a real one. So let's do one. You are going to have products on the top and reactants on the bottom. And one more thing that you need to know is that solids and liquids do not affect equilibrium, so they're not included in these equilibrium constant expressions. So we just ignore them. So let's look at this equation, example 1. We're going to look over at the product side, and I see Sn, but then I see a little s at the side of it. So this means this is a solid. We're just going to ignore it and skip over it. So I am going to come to the CO2, and it says it's a gas. So I'm just going to write CO2. And then because I have a coefficient in front of it, I'm going to raise that CO2 to the second. So what we're doing here is we're writing a little formula that we'll be able to put in our concentrations. Now on the reactant side, I also have a solid. So I'm just going to ignore it. We're just going to skip over it. And then I also have a gaseous reactant. So that's going to go on the bottom, CO, and I'm going to put it in brackets because it is in molarity. That's what Kc means. It means molarity units. Now my CO has a 2, and so I raise it to the 2. So this is just how you write the formula. You don't have to do anything else at this point. Just write the formula given the equation. So my Kc, my equilibrium constant expression, is equal to the concentration of the CO2 squared divided by the concentration of the carbon monoxide squared. Let's do another example. Again, if you see a KEQ, this is just a general. And most of the time, I'm going to ask you just to write the Kc, meaning molarity units. So again, we have products over reactants. So I'm going to have on my right-hand side in brackets SO3, and I'm going to square it. And I'm going to divide it by SO2, which is squared, and then O2, which is just all by itself. So this is just the formula, and these are all gases, so I can put them all in. So if you have a liquid or a solid, do not put those in. But if you have a gas or an aqueous solution, then that needs to be put in the formula. Let's do another example. We have our Kc. On the right-hand side, we have a NO2, and it's squared. And at the bottom, we have our N2O4, and it's just all by itself. Okay, so that's how you write that formula.